project, we estimated company Scope 1 and Scope 2 greenhouse gas emissions when direct measurements were missing. This matters for investors and regulators because they need a consistent way to compare climate risks across firms. We started with exhaustive data analysis across all the provided tables. We looked at distributions for revenue, ESG scores, environmental activity adjustments, and both targets, and found strong right skew and heavy tails, especially in revenue and emissions. We checked correlations and discovered a monotonic but nonlinear relationship between Scope 1 and Scope 2 after we calculated the Spearman and Pearson's correlation values, where we noted that the Spearman correlation was higher than the Pearson correlation. This indicates that as target Scope 1 increases, target Scope 2 also increases. The main pain points we identified after we merged all the files together were that there was a severe missingness in the environmental activities and SDG tables, extreme outliers in revenue and activity scores, and very high dimensionality in sector data and strong geographic heterogeneity by country. To handle the messy data, we applied data engineering to, for example, revenue. We used a log transform instead of capping, reducing skew while preserving rank information. For environmental activity scores, we capped values by activity type using percentiles to remove implausible extremes without necessarily erasing the high impact activities. We're not showing the improvements for the environmental data because we have 16. They're all located here. We also engineered richer features, PCA components on sector revenue distributions to compress over 200 NACE codes, aggregated activity statistics, and interaction terms such as revenue times, ESG scores, and country-level average emissions per revenue. We then tackled missing data with supervised imputation. We tried different approaches such as median, mode, mice, but the ones chosen had the best confidence scores. So gradient boosting models to infer environmental activity types, codes, and adjustments, and k-nearest neighbors to impute SDG commitments, both validated with cross-validation, like five-fold cross-validation, and confidence thresholds that you'll see here. For model selection and experimentation, we compared a couple. We compared random forest, XGBoost, CapBoost, and Elastic Net on the log transform targets. The tree-based models capture the non-linear relationships and interactions in our engineered features, while ElasticNet is good for offering interpretability and regularization on the linear side. After baseline comparisons, we chose CapBoost for Scope 1 due to its strong performance and stable generalization, and ElasticNet for Scope 2 for its balance of accuracy, simplicity, and speed that you can see here. We then performed hyperparameter tuning using randomized search, with cross-validation, exploring iterations, depth, learning rate, and regularization for CapBoost, an alpha and L1 ratio of overfitting to training only the features. This tuning phase improved the R-squared score and reduced overfitting, showing that we had a good command over the selected models rather than relying on the defaults of the models. And lastly, we evaluated the best models using R-squared, mean absolute error, and held out on the data. And our Scope 1 model explains over half of the variance and typically predicts within a factor of about 3 of the true emissions. Scope 2 performance is slightly lower, but it's still informative. We predicted the unknown values provided in the test and return results in the submission. And then from a business perspective, that level of accuracy is good enough for us to rank companies by the climate risk, flag potential regulatory issues, and support ESG screening and credit decisions, especially when combined with feature importance insights that highlight which sectors, countries, and ESG attributes drive emissions. We also implemented an application which my teammate Yaman is going to show you now.
On top of the ML model itself, we wanted to cater the entire process to everybody with any experience in this field. So like if you're like myself who has like experience in the field, it would be easier for you to look at the dashboard. So our product provides you a dashboard with each and every single process that we did. And this is a dynamic dashboard, so you can see different data points and understand them at your pace. Things like how many features did we engineer and what features we chose and how did we group them, right? Our model's performance, its calibration, like what the actual prediction, actual point was, and then what the predicted one was, the prediction distribution, and much more in detail, and information on what drives the predictions itself. Moreover, we also created a chatbot. What it does is it will help people like myself, even advanced people, to ask more questions after our presentation, right? You can ask more questions to the bot and it will explain the processes our different teammates made. So let's say I'm a beginner. I say, hey, I want to understand the process. Now, I'm not sure why it's all caps, but let's put that in. And it will take a little bit more time and it will explain hello and it will explain how the process worked. And Victoria is one of our teammates. We also have Maria. I believe it also talks about Maria's contribution and how they also did. So we have different approaches that we took and converged on the same answer or different answer. It explains all of those things. Thank you so much for your time.